What is dynamic programming? The main idea is to solve a large problem recursively by building from carefully chosen subproblems of smaller sizes. The optimal substructure property essentially says that we must choose subproblems in such a way that optimal solutions to subproblems can be combined into an optimal solution for the full problem. So as an example, what that means is if you are trying to find the best way to traverse through an array, you can do so by finding the best way to traverse through a certain part of the array, so to the certain position of the array. And if you're able to do that for every position of the array, by the time you get to the end of the array, you would have the best solution to the entire array itself. My favorite problem which outlines the strength of dynamic programming is House Robber 1, which is LeetCode problem 198, which essentially says that you are a professional robber planning to rob houses along a street. Each house has a certain amount of money stashed. The only constraint stopping you from robbing each of them is that adjacent houses have security systems connected, and it will automatically contact the police if two adjacent houses were broken into in the same night. Given an integer array nums representing the amount of money of each house, return the maximum amount of money that you can rob tonight without alerting the police. Well, the brute force solution to this problem would be to look at every home and decide, should I go rob this house or skip it? And do that for every single home until you have gotten solutions to every possible method and then choosing the best solution there. But the only problem, which is a huge problem, is that the time complexity is 2 to the power of n, because for every position you have 2 choices, and that just branches out like a really big tree. With dynamic programming, we can actually store the best solution up to the house that you're currently in, and then we will be able to use that solution for the next. This concept is called memoization. And by doing so, we can just loop through the array just one time, which gives us a time complexity of O of n. So let's try an example to try and understand this problem. So the problem that we are trying to solve is P of I, which is the most amount of money that we can solve to the ith position. And optimal solution to the ith position is the solution to the problem, the subproblem. And let's have a look at an example array so that we can see what we're dealing with. If these are the set of houses that we're given in the array nums, you can kind of see that by looking at it for a little bit, that the best solution is to take $5 and then $4 and results with a $9 profit. But how can we design an algorithm that can actually detect that? Well, let me make a second array which represents the optimal solutions up to each position, and we can have a look at the very first home. When you're on the very first home, you don't really have much of a choice but to take $5, but you start getting more choices towards the next home. So in house number 2, you either can take the amount of money in house number 2, or you can choose to take the amount of money that was the best solution to the previous home and stick with it. And you can see that taking $5, which was the previous solution, and keeping it is the better solution, even up to house 2. On house 3, you can do the same thing. You can either steal the current house and also 2 houses ago, because 2 houses ago is not adjacent, meaning we can still have taken the best solution to 2 houses ago. That would give me a value of 6, or I can skip my current home and take the best solution to the previous home, which was 5. But we can see that 6 is a better option, so we'll take that. In house number 4, we get the same options. We can either take house number 4 and the solution to 2 homes ago, which would be $9, or we can take the best solution to 1 house ago and stick with that. But you can see that 9 is better, so we're going to do that. And on the very last home, you can do the exact same thing. You either take the best solution to the previous, or take my current one and 2 houses ago, but you can see that both of them add up to 9, so that's alright. And the reason why both add up to 9 is because You can either take 5, 4 as your optimal solution, or you can actually go 5, 1, 3, which both yield $9. So then, what is the actual solution of optimal I? Well, we can see that from the example that we've just done, the optimal solution to the ith position makes us think about two cases. Case number 1 is the optimal solution to one house ago. Case number 2 is taking my current house and the optimal solution to two houses ago, and then taking the best solution out of the two. And that's exactly what the solution is. So you either take the optimal solution to one house ago, or you take the best solution to two houses ago and add that to the current house that you're on, and then you're going to take the maximum of these two solutions. So just as an extension, we can try code this problem up. But before we do so, you might have noticed that at any given index, I've only needed to look back 2 indexes. And essentially what that means is the full array that I had wasn't actually necessary. I only needed to look at 2 variables ago, the previous house and 2 houses ago. So we can actually further optimize this problem in terms of space complexity this time by only storing 2 variables. So let's actually try code this up. So 2 variables that I need to store is the best solution to one house ago and the best solution to 2 houses ago. And we're going to do that by best solution one house ago and best solution to 2 houses ago, and initializing both of them as 0. And then I'm going to loop through the nums array. But we actually need to have one temporary variable which stores the best solution. The best solution is going to be this right here, the maximum of one house ago or 2 houses ago and my current house. So 1 house ago or 2 houses ago plus current house, and the 2 houses ago will now become 1 house ago, and 1 house ago, which is as of now the house that I'm currently on, is going to be the best solution. And we can see that by the end of the array, opt1i is going to have the best solution, and we can return that, and it will yield the best space and time complexity, which we can see here. Okay, memory 34%. If we run one more time, hopefully it beats that. Sometimes the bit fluctuates a bit. Okay, there we go. Alright, and that's how you do house robber and dynamic programming.